Does the universe mourn its dead? It seems an absurdly human question to ask of such an ancient and indifferent darkness. Yet every single second across the unfathomable tapestry of the cosmos, nearly 4,000 stars extinguish their fires. 4,000 colossal engines of creation, each one a sun, each one potentially the anchor of its own family of worlds, simply cease. Their light, which may have travelled for 100 million years to reach us, becomes a ghost. It is an echo of a life that has already ended, a final postcard from a long-vanished shore. We are in every sense living in a graveyard of light surrounded by the luminous memories of the departed. For millennia we looked up and saw eternity. We saw permanence in the celestial clockwork, a divine and unchanging architecture. But we were mistaken. The heavens are not a static monument. They are a living, breathing and dying ecosystem on a scale that defies our comprehension. Each point of light is a story with a beginning, a middle, and a violent or profoundly quiet end. Some, the true titans of the cosmos, die in the grandest spectacle the universe can muster, a supernova. In a final, defiant roar, they forge the heaviest elements in their thermonuclear hearts and blast them across interstellar space. They seed the void with the very building blocks of future stars, of planets, and of us. Their death is a form of cosmic reincarnation, a sacrifice that makes new life possible. From their ashes, new worlds are born. But what of the others? What of the overwhelming majority of stars, the quiet and diligent workers of the galaxy, like our own sun? They're too small, too modest to go out in such a blaze of glory. They lack the sheer gravitational menace to collapse into the infinite density of a black hole, or the explosive fury to rip themselves asunder. For them the end is not a bang, but a slow, inexorable sigh. They swell and burn through their final reserves of fuel, becoming bloated incandescent giants, before puffing their outer layers away into beautiful ghostly nebulae. They are the fading embers of the cosmic hearth, leaving behind only their impossibly dense cooling cores. These stellar remnants, these white dwarfs, are the most common form of stellar corpse. They are cosmic ghosts packing the mass of a sun into a sphere no larger than the Earth. They are the silent, forgotten headstones in that celestial graveyard. And it is here, in the quiet dignity of this stellar death, that the universe performs its most patient and unbelievable act of alchemy. It is here that we are forced to confront a conclusion so startling, so contrary to our everyday experience that it sounds like a myth whispered from the future. What truly becomes of these stellar hearts after an eternity of cooling? What is the final, ultimate form of matter when left to the slow, patient hand of universal law? The answer for these specific stars is not dust. It is not a perpetually fading ball of gas nor a lightless void. It is something solid, something ordered, something perfect. The ultimate state of these dying suns, the final product of their multi-billion-year lives, is a diamond. A single planet-sized crystal of carbon and oxygen forged not in the fires of a stellar core but in its cooling ashes. A monument of perfect interlocking atoms stretching for thousands of miles, shimmering with a ghost light in the eternal dark. This is not a metaphor. It is not science fiction. It is the literal physical destiny awaiting trillions upon trillions of stars across our galaxy alone. The most enduring, most valuable, and most perfect structure we know on Earth is, in the grand scheme of things, the universe's preferred tombstone. A celestial gemstone of such purity and magnitude that it would make every diamond on our planet seem like a single grain of insignificant sand. An object where the chaotic, fiery heart of a star has finally found peace in a state of absolute crystalline order. It is the universe's ultimate act of transformation, turning the engine of light into a monument of permanence. It is a process that transmutes a star's very essence from a raging thermonuclear furnace into a cold, dark, and unimaginably beautiful jewel. Now you are right to be skeptical. Your mind, grounded in the realities of human experience, should be screaming a single powerful question around how could we possibly know this? The sheer audacity of the claim seems to border on the absurd. We have never held such an object. We have never seen one up close. And this leads us to the central paradox of our story, a challenge so immense it makes interstellar travel look trivial. The process of crystallization, the slow, methodical settling of atoms from a superdense plasma into a perfect lattice is governed by temperature. As the white dwarf radiates its leftover heat into the void, it cools. But the timescale for this cooling is something for which we have no human frame of reference. It is a span of time so colossal, so far beyond our own existence, that it renders the entire history of our species into less than a single heartbeat. The universe itself is currently about 13.8 billion years old. A sun-like star will take perhaps 10 billion years to exhaust its fuel and become a white dwarf, but for that white dwarf to cool down sufficiently to begin the process of crystallization and fully transform into a diamond star, that takes quadrillions of years. Not billions, quadrillions, 1,000 trillion years, 1,000. An age so profound that it is hundreds of thousands of times longer than the current age of the entire universe. Let that sink in. We're talking about a future so distant that the galaxies themselves will have merged and scattered. The great cosmic web will have evolved into something unrecognizable. The very last embers of star formation will have long since faded out, leaving a cosmos populated only by stellar remnants, black holes, and the deepening cold. The transformation we seek to witness has therefore almost certainly not happened yet. Anywhere. We are the astronomers of an infant universe looking at stellar corpses that are still far too young and far too hot to have completed their final metamorphosis. We are trying to study the final form of a mountain by observing a single grain of sand roll down its slope. We are trying to understand the full life of a redwood by watching it for the blink of an eye. So how can we claim to observe an event that is not yet visible? How can we construct a documentary in what we are calling scientific real time about a process that has not and will not reach its conclusion until the universe is an unrecognizable wasteland of time? This is the grand challenge, and the answer is that we have invented a new kind of seeing. We have built an observatory that is not merely made of mirrors and lenses, but of logic data and immense computational power. We have learned to bridge the impossible gulf of cosmic time by weaving together three distinct pillars of human ingenuity, creating a revolutionary way to witness the future. Our journey begins with the first pillar, modern astronomy, our eyes on the cosmos. For decades, we have been meticulously cataloguing the heavens, turning our most powerful telescopes toward these faint stellar ghosts. Instruments like the Hubble Space Telescope, the Gaia spacecraft, and the Kepler mission have become our celestial cartographers, mapping the locations, movements, and properties of countless white dwarfs. We can collect their faint ancient light and dissect it with breathtaking precision. From that light, we can deduce their temperature, telling us how long they have been cooling. We can determine their mass, which dictates the immense pressure within their cores. And most remarkably, we can detect subtle pulsations, tiny quakes running through the star's structure. This field, known as astroseismology, allows us to effectively perform a cosmic ultrasound, peering deep beneath the surface to understand the composition of the star's heart. Is it primarily carbon-oxygen? A mixture of both, these telescopes provide us with the essential starting conditions. They give us the before picture, a snapshot of a white dwarf, as it exists today, a single frame in a movie that will last for quadrillions of years. They provide the raw data, the vital clues from the scene of a star's death, which we can then feed into our grand simulation. Without this direct observational evidence, everything that follows would be pure speculation. This is our anchor to reality. But having a picture of the present is not enough. To understand where these stars are going, we need the second pillar, the fundamental laws of physics, the universal rule book. This is the accumulated knowledge of generations of scientists working in laboratories here on Earth, who have deciphered the behavior of matter under the most extreme conditions imaginable. Through quantum mechanics, we understand how atoms bond and arrange themselves. Through thermodynamics, we understand the flow of heat and energy, the very engine of change. And through high-pressure physics, using diamond anvil cells that can replicate the crushing forces found deep inside planets, we have studied how elements like carbon behave when squeezed with unimaginable force. We have learned from these earthbound experiments the precise temperature and pressure at which a fluid of carbon and oxygen will give up its chaotic freedom and lock itself into a rigid crystalline lattice. These laws are universal. The physics that governs the formation of a tiny diamond in a laboratory in California is the same physics that will one day govern the formation of a planet-sized diamond in the heart of a dying star 100 light-years away. This is our Rosetta Stone. It gives us the syntax and grammar of the universe, allowing us to translate the raw data from our telescopes into a predictive narrative. We know the starting point, and now we know the rules of the journey. This brings us to the final and most crucial pillar of our endeavour: computational power, our virtual time machine. This is where the magic happens. This is how we leap across the chasm of quadrillions of years. We take the real-world data from our telescopes, the temperature, mass, and composition of a specific white dwarf. We then program the immutable laws of physics, the rules of thermodynamics and quantum crystallization into the world's most powerful supercomputers. We build a perfect digital twin of the star as it exists today, a universe in a box. And then we press fast forward. These computational engines, capable of trillions of calculations per second, can simulate the cooling of that star over cosmic eons. They can model atom by atom how the immense pressure organizes the star's core, how the slow radiation of heat changes its internal state, and precisely when and how the first seed crystals begin to form. We can watch as the crystallization front slowly, inexorably sweeps outwards from the core over millions and billions of simulated years. We can see the chaos of the plasma give way to the perfect order of the diamond lattice. We are in effect compressing a quadrillion years of physics into a few weeks of computation. This is our scientific real time. It is not an observation made with the human eye, but an observation made with the unerring eye of mathematics. It is a simulation so deeply grounded in real-world data and fundamental laws that it becomes the closest thing we can have to a direct view of the deep future. This powerful trinity of observation, theory, and simulation has given us a new form of perception. It has gifted us the ability to see the unseen, to witness the unwitnessable. It allows us to stand here in the cosmic dawn and watch the fate of stars that will unfold in the universe's final twilight. This documentary is the story of that impossible observation. We will take you on a journey through each of these pillars of discovery. We will show you the telescopes that hunt for stellar ghosts. We will take you into the laboratories that replicate the crushing heart of a star. And we will fly you through the virtual universes inside our supercomputers, where you will see a sun metamorphose into a diamond before your very eyes. We have built a new kind of telescope, a telescope that looks not just across space but through time itself. And now we are pointing it at the ghost of a dying star. Our journey begins not in the cold vacuum of space, but deep within the star itself, at the moment its great heart falls silent. For we must first understand the death before we can witness the final crystalline resurrection. The universe's most magnificent jewel is not born in darkness. It does not form under the crushing pressure of a planet's mantle. Instead, its genesis is a paradox of unimaginable scale. It begins its life in the heart of an immense celestial fire, and it is forged only when that fire finally inevitably dies. To understand this cosmic alchemy, we must first look to the cradles of creation. We must journey back to a time before the fire, to the vast, cold and silent clouds that drift between the galaxies. Out here in the interstellar medium float enormous ethereal structures. They are the stellar nurseries, the cosmic wombs known as molecular clouds. Spanning light years, these are not clouds of water vapour like those on Earth. They are impossibly tenuous veils of hydrogen gas and microscopic dust, colder than anything you have ever experienced. Here darkness and quiet reign supreme for millions, even hundreds of millions of years. But within this serene expanse, a silent, patient force is at work. Gravity. It is the grand sculptor of the cosmos, a force that given enough time is relentless. It begins to pull these diffuse filaments of gas and dust together. At first, the process is imperceptibly slow, a cosmic ballet of drifting particles. But as matter congregates, its collective gravitational pull intensifies. What was once a gentle gathering becomes a determined collapse. Countless pockets within the cloud begin to shrink to contract under their own immense weight. Each collapsing pocket is a stellar seed, a protostar in the making. As the cloud fragment compresses, something extraordinary begins to happen. The particles within it, squeezed ever closer, collide with increasing frequency and violence. Friction generates heat, and the cold heart of the cloud fragment begins to glow. It awakens first with a dull infrared glimmer hidden from visible sight. This is the embryonic stage of a star, a glowing sphere of gas called a protostar. It is not yet a true star. It is a body caught in a titanic struggle. Gravity continues its inexorable crush, attempting to collapse the protostar into an ever smaller point, but the rising temperature and pressure at its core begin to fight back, pushing outward. For thousands of years, the battle rages within this nascent object. The core becomes a crucible of unimaginable conditions. The temperature climbs past millions of degrees Celsius. The pressure builds to a level that would pulverize any material we know on Earth. The atoms of hydrogen, the most basic element in the universe, are stripped of their electrons. They become a superheated plasma, a chaotic soup of protons and electrons. And then the universe holds its breath. A critical threshold is crossed. The temperature and pressure become so extreme that they overcome one of the most fundamental forces of nature. They defeat the electromagnetic repulsion that keeps positively charged protons apart. Protons, which have spent their existence pushing away from one another, are slammed together with such force that they fuse. In that cataclysmic instant, a new element is born. Hydrogen nuclei merge to become helium, and in this act of nuclear fusion, a tiny fraction of their mass is converted directly into a colossal burst of pure energy. A light is switched on in the cosmos. The protostar has ignited. It has become a star. This outward torrent of energy born from the nuclear furnace in its core provides the final definitive counterpunch to gravity's inward crush. The star settles into a stable, magnificent equilibrium, a perfect balance between two opposing titans. This state of grace, this celestial truce, is called the main sequence. And for a star like our Sun, this is the beginning of a long and placid adulthood. For the next 10 billion years, the star will be a bastion of stability. Its nuclear heartbeat will pulse with a steady, unwavering rhythm. Deep within its core, it will relentlessly fuse 600 million tons of hydrogen into helium every single second. This is not a violent, uncontrolled explosion, but a perfectly self-regulating engine. If the fusion rate were to increase slightly, the core would expand and cool, slowing the reaction back down. If the rate were to drop, the core would contract and heat up, accelerating the reaction once more. It is this elegant feedback loop that allows stars like our Sun to shine with such serene constancy for eons. It is during this long, predictable summer that the true magic of a solar system can unfold. The star becomes a gravitational anchor holding planets in its gentle sway. It bathes them in a life-giving stream of light and heat. It provides the energy that can drive chemistry, warm oceans, and perhaps, just perhaps, spark the intricate phenomenon we call life. Everything you see around you, the very atoms in your body that are not hydrogen and helium, were forged in the hearts of stars that lived and died before our Sun was even born. We are in the most literal sense the children of this stellar fire. But this tranquil existence cannot last forever. Every second of its life, the star is converting its primary fuel, hydrogen, into a heavier element, helium. The core, once a pure reservoir of hydrogen, slowly becomes polluted with this helium ash. For billions of years, this ash is inert, simply accumulating at the center, unable to fuse at the current core temperatures. The star is in effect slowly running out of fuel where it needs it most. A crisis is looming, an energy catastrophe written into the laws of physics from the moment of the star's birth. And after some 10 billion years of steadfast shining, that crisis arrives. The hydrogen in the very center of the core is finally exhausted. The nuclear furnace, which has raged for an eternity, sputters and falls silent in the heart of the star. For the first time in its life, the outward push of fusion energy falters. Gravity, the star's lifelong adversary, senses weakness, and it seizes its advantage with devastating consequences. The helium ash core, no longer supported by fusion pressure, begins to collapse under its own colossal weight. This gravitational collapse is a cataclysmic event. As the core crushes inward, its temperature and density skyrocket to previously unseen levels. This intense heat radiates outward into the layers of gas surrounding the dead core. It heats a shell of pristine unused hydrogen until that shell reaches the critical temperature for fusion. A new fire is lit, but this one is different. It is not a steady, stable burn in the deep core. It is a frantic, desperate inferno raging in a shell around a collapsing center. This shell-burning fusion is far more intense, far more furious than anything the star has experienced before. It unleashes a flood of energy that pushes outward with unimaginable force, and the star begins to swell. Its outer layers, pushed by this raging internal furnace, expand to monstrous proportions. The star's surface cools as it expands, shifting its colour from a brilliant yellow-white to a dull, ominous red. It transforms into a red giant. This is not the gentle, life-giving star of the main sequence. This is a bloated crimson tyrant, a grotesque parody of its former self. Its diameter swells 100-fold, even 1,000-fold. It becomes so large that it can engulf the orbits of its own inner planets, swallowing and vaporizing the very worlds it once nurtured. Our own sun will one day undergo this same violent metamorphosis. In about 5 billion years, it will swell to consume Mercury, then Venus, and quite possibly the Earth itself. Our world will be scoured clean by its progenitor, its oceans boiled away, its continents melted into a sea of magma. The star that gave us life will be the agent of our planet's utter annihilation. The red giant phase is a star's chaotic and violent death throe. The shell burning is unstable, leading to massive fluctuations in energy output. The star pulses and throbs, its delicate equilibrium shattered forever. Powerful stellar winds, like a continuous hurricane, begin to blow from its surface. They carry away huge quantities of the star's outer atmosphere, casting it off into the surrounding space. This process of shedding its outer layers is slow and agonizing. Over thousands of years, the star loses a significant fraction of its total mass. Then, in a final series of convulsions, the star experiences thermal pulses. These are gigantic burps of energy from the unstable interior. Each pulse is a final shuddering sigh that pushes the remaining outer envelope of gas away from the dying core. The star is quite literally coming apart at the seams. What it leaves behind is one of the most beautiful and ephemeral sights in the entire cosmos, a planetary nebula. The name is a historical misnomer. It has nothing to do with planets. Early astronomers viewing these objects through small telescopes thought they resembled the faint hazy disks of gas giants. But what they truly are is the star's luminous ghost. The cast-off layers of gas rich with elements like carbon, nitrogen and oxygen, cooked inside the star, expand outward into a vast glowing shell. This shell is illuminated from within by the incredibly hot, now exposed core of the star. The intense ultraviolet radiation from this central remnant energizes the gas, causing it to fluoresce in spectacular vibrant colors. We see intricate structures, cosmic Rorschach tests sculpted by magnetic fields, and the dynamics of the expanding gas. There are rings, lobes, and delicate wispy filaments stretching across light years of space. Each one is a unique celestial flower, a final breathtaking monument to the star that was. But this beauty is tragically short-lived. In just a few tens of thousands of years, a mere cosmic instant, the nebula will expand and fade. Its gases will dissipate, mingling with the interstellar medium, enriching it with the heavy elements needed to form new stars, new planets, and perhaps new life. It is a poignant and beautiful act of cosmic recycling. As the vibrant veil of the planetary nebula thins and drifts away, our attention is drawn to the object left at its heart. The stage is cleared for the final actor in this long drama, and what is revealed is one of the most extreme and bizarre objects in the universe. The stellar core stripped bare, the white dwarf. This is the end of the line for a star like our Sun. It is the smouldering ember left behind after the great fire has gone out. But do not let the term ember fool you. This is an object of almost unbelievable physical properties. It is incredibly small, typically no larger than the planet Earth. Yet compressed within that tiny volume is the mass of an entire star. It has the mass of our Sun packed into a sphere 1,000,000 times smaller. The gravitational field at its surface is hundreds of thousands of times stronger than Earth's, and its density is simply staggering. A single teaspoon of white dwarf material, if you could somehow bring it to Earth, would weigh more than an elephant. A matchbox full would outweigh a mountain. This is matter, unlike anything we know in our everyday lives. The star's immense gravity has crushed its atoms so completely that their electrons have been forced out of their normal orbits. The electrons are squeezed together as tightly as the laws of quantum mechanics will allow. This creates a bizarre state of matter, known as electron-degenerate matter. The electrons form a rigid crystalline lattice, an almost perfect incompressible structure. They generate a powerful outward pressure, a quantum mechanical pressure that finally definitively halts any further gravitational collapse. The star is now an atomic tomb stable, not because of the fire of fusion, but because of the strange rules of the quantum world. And it is fantastically hot. When it is first born from the heart of its planetary nebula, a white dwarf's surface temperature can exceed 100,000 degrees Celsius. It glows with a brilliant white-hot intensity, a celestial blowtorch pouring searing ultraviolet radiation into space. But this heat is purely residual. It is leftover energy from its life as a star and its violent collapse. There is no new energy being generated within it. The nuclear fires are extinguished forever. The white dwarf is a cosmic cinder, a stellar ghost that has only one fate ahead of it. An extraordinarily long, slow journey into darkness. It has become a celestial battery with a finite amount of thermal energy, and for the rest of its existence it will do nothing but radiate that energy away into the cold vacuum of space. This cooling process is the longest, most protracted phase of its entire existence. It will take billions, even trillions of years for a white dwarf to shed all its heat. Trillions of years. A timescale so vast it dwarfs the current age of the universe itself. We are looking at a process that will play out in the far deep future, long after the last stars in the cosmos have faded. And it is during this unimaginably slow cooling, this gradual descent into absolute zero, that the final, most spectacular transformation begins. The star's last secret is about to be revealed. For as the heat bleeds away into the void, the carbon and oxygen atoms within that degenerate core begin to settle. They lock into place, and within that cooling ember a new kind of miracle begins to take shape, and so the stellar fire is extinguished. What remains is not a corpse in the way we understand it, but a ghost. A searingly hot, city-sized ember left to drift among the cosmos, a monument to a life of fusion and fury. Before you is the newborn white dwarf, a brilliant point of light hanging in the centre of its own funeral shroud. It is one of the most extreme objects you will ever encounter, an entity teetering on the very edge of physical possibility. Its gravitational pull is ferocious, 1,000,000 times stronger than what you feel on Earth. If you could stand on its surface, you would be crushed into a microscopic smear by forces that beggar belief. A single teaspoon of its material would outweigh a fleet of battleships, its atoms packed together with a violence that defies all earthly intuition. This incredible density poses the most immediate question: why is it still here? With its internal furnace switched off, with no thermonuclear reactions, pushing outward against the relentless inward crush of its own gravity, what prevents this stellar remnant from collapsing completely? What stops it from shrinking further, perhaps into the infinite pinprick of a black hole? The answer is not found in the familiar physics of heat and pressure that governed its life as a star. It is found in a realm far stranger, a place where the fundamental rules of matter itself manifest as an invincible, invisible shield. The universe, it turns out, has one last trick up its sleeve. To understand this celestial standoff, you must journey deep inside the white dwarf, past its thin atmosphere of hydrogen and helium, and into its core. Here you will find no atoms in the conventional sense. The immense pressure has stripped the electrons away from their atomic nuclei, creating a bizarre state of matter known as a degenerate plasma. Imagine a sea of free-roaming electrons moving at nearly the speed of light, weaving between a fixed array of carbon and oxygen nuclei. Gravity continues its inexorable siege, attempting to force these particles ever closer. It tries to squeeze the electron sea to compress it into a smaller and smaller volume. But here it encounters a law more fundamental than its own ambition, the Pauli exclusion principle. This is not a force in the classical sense, not like magnetism or gravity. It is a quantum mechanical decree, a rule woven into the very fabric of reality that states two identical electrons cannot occupy the same quantum state, the same address, the same energy level at the same time. Think of it as the universe's most extreme game of musical chairs. As gravity tries to shove more electrons into a confined space, the chairs fill up. To avoid sitting in an occupied seat, electrons are forced into higher and higher energy levels, making them move faster and faster. This frantic high-speed motion generates an immense outward pressure, a purely quantum phenomenon called electron degeneracy pressure. It is a repulsion born not of charge but of existence itself, a subatomic declaration that there is a limit to how much matter can be compressed before it says no more. This quantum bulwark is astonishingly powerful, a testament to the strange and potent laws that govern the subatomic world. It is the only thing standing between the mass of a sun and total collapse. Without it, every white dwarf in the universe would have winked out of existence the moment its nuclear fires died. For all its might, however, this pressure does not generate new energy. It is a static defense, a perfect stalemate against gravity's unending assault. And so the white dwarf enters the longest and most serene phase of its existence, the long goodbye. It is now a cosmic thermos, a sealed container of immense residual heat left over from its life as a star and its violent gravitational collapse. But it is not a perfect thermos. Through its thin, non-degenerate atmosphere, this trapped energy slowly, painstakingly leaks out into the cold vacuum of space. It radiates away its life savings of heat not as a brilliant blaze, but as a faint ethereal glow. The process is fantastically slow. The surface area of a white dwarf is tiny, only about the size of our planet, so the rate of heat loss is agonizingly gradual. The journey from a searingly hot blue-white remnant to a cooler yellow-white glow takes billions of years. Billions more to fade to orange, then to a dull cherry red. We are watching the universe's slowest sunset, a thermal whisper that will persist for longer than the current age of the cosmos itself. Our own universe is only about 13.8 billion years old. This is barely enough time for the very first white dwarfs that ever formed to have cooled to a few thousand degrees. Their full cooling journey, the path to becoming a cold, invisible black dwarf, will take trillions of years, hundreds of times longer than the universe has yet existed. They are cosmic clocks, their temperatures a direct measure of the time that has passed since their parent stars expired. By studying them, we can read the history of star formation in our galaxy, tracing the echoes of stellar births that occurred in the distant past. But this slow, stately process of cooling hides a secret. It masks a transformation so profound, so utterly unexpected that for decades it was considered little more than a theoretical fantasy. As the white dwarf continues to shed its heat, the kinetic energy of the particles within it begins to dwindle. The carbon and oxygen nuclei, which were once jiggling and vibrating furiously in the superheated plasma, begin to slow down. Their thermal motion, the thing that kept them in a disordered, fluid-like state, is no longer strong enough to resist the powerful electrical forces between them, and when this happens, something remarkable is predicted to occur. The same process that turns liquid water into a solid ordered crystal of ice on a cold winter's night begins to take hold in the heart of the dying star. The carbon and oxygen nuclei under pressures 1,000,000 times greater than those at the centre of the Earth begin to lock into place. They arrange themselves into a vast repeating three-dimensional lattice. The stellar core begins to freeze. This is not freezing as we know it. There is no gentle dusting of frost. This is a phase transition on a scale that is difficult to comprehend. A wave of crystallization starting at the centre where the pressure is highest is thought to sweep outwards, converting the fluid plasma into a solid monolithic crystal. And what is a crystal of carbon formed under unimaginable pressure? Here on Earth we have a name for it: a diamond. The theory was breathtaking in its audacity. It suggested that hidden within these faint stellar embers was an object of almost mythical quality, a diamond the size of a planet, an orb of crystallized carbon and oxygen weighing as much as our sun. The ultimate cosmic jewel forged not in a jeweller's workshop but in the heart of a dead star. This wasn't merely a poetic notion. It was a direct mathematical consequence of applying the laws of condensed matter physics to the extreme environment of a white dwarf interior. The calculations first performed in the 1960s were elegant and compelling. They showed that as the temperature dropped below a certain threshold, the star's core would have no choice but to crystallize. It was an inevitable final state, the logical endpoint for the matter within these stellar remnants. The physics was sound, the prediction unambiguous. A sky full of diamonds was no longer just a line in a song. It was a scientific hypothesis. But a beautiful theory, no matter how elegant, is merely a ghost in the world of science until it is confronted with observation. And here astronomers faced a chasm of difficulty that seemed almost insurmountable. How could you possibly prove that a star trillions of miles away had a solid crystalline core? You cannot send a probe to drill into its surface. You cannot bounce seismic waves through its interior, as we do to study the Earth's core. The evidence would have to be subtle, an indirect clue hidden in the faint light that reaches our telescopes across the gulf of interstellar space. The first and most obvious challenge was the sheer timescale of the process. Crystallization is predicted to begin only after a white dwarf has been cooling for billions of years. This means that only the oldest, and therefore the dimmest white dwarfs, would be candidates for this transformation. Astronomers were being asked to find the faintest needles in the vast cosmic haystack objects, so ancient and faint they are at the very limit of our detection capabilities. These are the true ghosts of the galaxy, their light a barely discernible glimmer against the backdrop of infinity. Finding them in sufficient numbers to study as a population was a Herculean task in itself, requiring deep patient surveys of the sky that pushed technology to its absolute limits. Even if you could find them, the second challenge was even more profound. What would you look for? The crystallization itself is an internal process hidden from direct view beneath the star's atmosphere. The initial theoretical models, however, offered a tantalizing clue, a potential observational signature. The process of crystallization, like the freezing of water, is exothermic. It releases a small amount of energy known as latent heat. As the wave of crystallization sweeps through the white dwarf's core, this slow release of energy should act like a secondary temporary power source. It wouldn't be enough to make the star brighten, but it should be enough to momentarily pause its cooling. For a period of perhaps 1 billion years, the crystallizing white dwarf would cool more slowly than a similar star that was not crystallizing. This predicted slowdown, this plateau in the cooling sequence, became the theoretical smoking gun. If astronomers could meticulously measure the temperature and luminosity of a large population of white dwarfs of different ages, they should find a pile-up and excess of stars at a specific brightness. This stellar traffic jam would correspond to the age at which crystallization kicks in, holding the stars at that luminosity for longer than expected, before allowing them to resume their fade into darkness. For decades, this remained the frontier of the field. A grand confrontation was quietly brewing between a stunning prediction and the stark reality of the observable universe. On one side, you had the theorists with their elegant equations and compelling models of stellar interiors confidently predicting the existence of these incredible cosmic diamonds. On the other, you had the observers battling against the faintness of their targets and the subtle nature of the evidence they were seeking. The early searches were inconclusive. The data was noisy, the number of known old white dwarfs too small. There were hints, tantalizing suggestions in the plotted data, but nothing definitive. A deep sense of uncertainty lingered. Was the theory correct? Was the universe truly manufacturing these colossal gems in the dying embers of stars? Or was there some piece of physics that had been missed, some unknown process that prevented crystallization from ever occurring? The prediction of a star turning into a diamond was one of the most romantic and awe-inspiring ideas in modern astrophysics, a perfect marriage of fundamental physics and cosmic grandeur. But without proof, it was just that, an idea. The silence from the sky was deafening. The universe was holding its secrets close, forcing us to wonder whether these planet-sized diamonds were a reality or destined to remain forever as a gleam in the theorist's eye. The stage was set for a discovery, for a breakthrough that would require new instruments, new techniques, and a new way of listening to the whispers of the dying stars. The hunt was on, so the equations balanced. The physics stood on a foundation of unassailable logic, predicting a future for these stellar embers that was as beautiful as it was bizarre. A heart of diamond forged in the dying breath of a sun. For decades, however, this cosmic jewel remained a ghost in the machine of astrophysics, a breathtaking prediction spun from pure quantum mechanics, yet utterly beyond the grasp of our instruments. It was a tantalizing, frustrating truth locked away in an impenetrable vault. How do you prove the impossible? How do you map the core of a star 100 light-years away, a body so dense a single spoonful would outweigh a mountain? We could see their light, measure their temperature, and weigh their immense gravity, but their deep interiors remained a realm of pure inference. The diamond was a phantom, a whisper in the mathematics. To turn that whisper into a roar, We needed a witness. We needed a way to peel back the layers of incandescent gas and stare into the furnace itself. We needed a breakthrough, and it came as scientific revolutions so often do not with a triumphant shout, but from a quiet, unassuming corner of the sky. It arrived in the form of a strange new class of stellar remnant catalogued as ZZ-CT stars. These were not the stable, steadily cooling white dwarfs we'd grown accustomed to. These were different. They were restless. Observers noted that their light wasn't constant. It pulsed. Over periods of just a few minutes, these tiny ancient stars would brighten and dim with an almost perfect hypnotic rhythm. They were breathing, shimmering, beating like a distant heart. Initially, this was just another cosmic curiosity, a puzzle for theorists to unravel. What internal engine could drive such a rapid, gentle oscillation in an object that should be settling into a quiet, eternal retirement? Was it some magnetic instability, a remnant of its former life? Or was it something else? Something deeper? Nobody yet knew that in these subtle celestial flickers, the universe was handing us the very key we'd been searching for. We were seeing the first hints of a new science, a way to turn the entire star into a musical instrument, and listen to the symphony playing out within its core. This revolutionary idea is known as astroseismology. The name itself suggests its power, the study of starquakes. Just as geologists on Earth use the waves from an earthquake to map our planet's hidden layers, the crust, the mantle, the liquid outer core and the solid inner core, astronomers realized they could do the same with stars. A star is not a perfectly rigid object. It's a colossal sphere of gas and plasma constantly churning, ringing with vibrations that travel through it. These vibrations, these starquakes, are known as pulsation modes. Some waves travel deep, bouncing off the dense core before returning to the surface. Others skim just beneath the star's skin. Each of these waves carries information. Each one is a messenger bringing a dispatch from the abyss. By rippling to the surface, these waves subtly alter the star's shape and temperature, causing the very rhythmic changes in brightness that we observe from Earth. The star becomes a cosmic bell. If you can measure the precise frequencies of its ringing, the fundamental tones, and all the complex overtones, you can deduce the internal structure that creates them. You can determine the bell's size, its density, its composition, and even the shape of the clapper striking from within. These pulsating ZZ-CT stars were not just flickering, they were broadcasting their internal blueprints across the void. We had for the first time a way to conduct reconnaissance on the interior of a white dwarf without ever leaving home. The task was monumental, requiring a patience bordering on the sublime. For years, astronomers trained their telescopes on these stellar metronomes recording every minute fluctuation in their light. The signals were infinitesimally small, a change in brightness of less than 1% easily lost in the noise of Earth's own atmosphere. Yet night after night the data accumulated, building a library of stellar heartbeats. Each pulsation mode was dissected, its frequency measured with astonishing precision. Computer models were built virtual white dwarfs created inside supercomputers, where physicists could tweak the parameters, the mass, the temperature, the composition, and see if they could replicate the exact song being sung by the real star. It was like trying to recreate a grand piano sight unseen just by listening to a single, complex chord played from 1,000,000 miles away. For a long time, the models and the observations matched beautifully. The rhythm of the pulsations told us about the star's thick helium atmosphere, its deeper carbon-oxygen interior, and its overall mass. But as the data grew more refined, a stubborn anomaly began to emerge from the noise. There was a persistent, subtle deviation that the standard models simply could not explain. Something was wrong, or rather something was different. The pulsations were telling us a story our theories hadn't yet accounted for. One of the most powerful predictions of astroseismology relates to how the pulsation frequencies should change as the star cools. Like the strings of a cooling piano slowly losing their tune, the pulsation periods of a white dwarf should drift in a smooth, predictable way over thousands of years. This change is far too slow to observe directly in a human lifetime, but the theory provided another more immediate test. It predicted that if a white dwarf's core began to crystallize, the process would have two dramatic observable effects on its pulsations. The first consequence would arise from a simple, elegant piece of physics. When a liquid freezes, it releases energy. You've seen this yourself. It's why oranges in a grove are sprayed with water to protect them from a frost. As the water freezes on the fruit, it releases a tiny amount of latent heat, keeping the orange just warm enough to survive. Now, imagine that process on a stellar scale. As the liquid carbon core of the white dwarf begins to lock into a solid diamond lattice, it releases a tremendous surge of latent heat. This energy percolates up through the star, creating an internal heat source that temporarily slows its cooling. A crystallizing white dwarf would therefore appear younger and hotter than its true age would suggest. It would be a star with a secret furnace burning in its heart. This pause in cooling, this momentary defiance of entropy, would be the first clue. An astronomer charting the temperatures and ages of a population of white dwarfs would suddenly find a cluster of them that seemed to be lagging behind, refusing to grow cold at the expected rate. Their evolutionary clocks would appear to be running slow. But the second piece of evidence was even more direct, encoded within the stellar music itself. The sound waves resonating inside the star would behave differently depending on what they travelled through. A wave moving through a liquid plasma travels at as different speed than a wave moving through a dense solid crystal. As the solid diamond core grew from the centre outwards, it would begin to alter the resonant cavity of the entire star. It would be like a cello slowly filling with glass from the inside out. The tones it could produce, the harmonies it could sustain, would inevitably change. Specifically, some pulsation modes that travelled deep into the core would become trapped, unable to propagate through the newly formed solid. These frequencies would simply vanish from the star's pulsation spectrum. Other frequencies would be subtly shifted as the sound waves had to travel around this growing crystal obstacle. The very character of the star's song would be rewritten by the metamorphosis happening in its core. And that is precisely what astronomers began to find. They found entire populations of ZZ-CT stars that were demonstrably hotter and brighter than they should be, their cooling held in stasis by that slow release of latent heat. This accounted for the anomalous populations that had puzzled scientists for years. The data points on their graphs were not errors, they were evidence. Then, by comparing the pulsation spectra of many different white dwarfs at different temperatures, they saw the predicted pattern emerge. The hotter, younger, fully liquid white dwarfs displayed a rich chorus of pulsation modes. But when they looked at the slightly cooler ones precisely in the temperature range where crystallization was predicted to begin, certain deep travelling frequencies were conspicuously absent. The stellar bell had been muffled from within. The deeper notes in its song had been silenced. It was the ultimate smoking gun. We couldn't see the diamond core directly, but we could see its shadow cast in the language of vibration and light. We could see the empty spaces it left behind in the star's music. This was no longer speculation. The subtle flicker of these distant stars, once a mere curiosity, had become the first compelling observational proof that the universe was indeed capable of forging something so extraordinary. The theory had been transformed into a testable, verifiable reality. The ghost in the machine had begun to take solid form. We had learned how to listen for the sound of a star turning to crystal, and for the first time across the vast silent expanse of space we were finally hearing it. And so the idea was no longer just a flicker of theoretical genius, a beautiful equation on a blackboard. It was a breathtaking, terrifying possibility. That deep within the silent graveyards of the cosmos, the cold hearts of dead stars were slowly, inexorably turning into structures of unimaginable size and perfection. Crystalline spheres of carbon and oxygen, diamonds the size of planets. But a possibility, no matter how elegant, is not proof. The initial evidence that subtle delay in the cooling of certain white dwarfs was like finding a single anomalous footprint in a vast unexplored desert. It pointed to a fantastic creature, but told us nothing of its nature, its life, its true form. The scientific community, captivated but cautious, now faced a truly monumental challenge. How do you prove a process that takes billions of years to unfold? We, with our fleeting lifespans, are but mayflies trying to comprehend the life of an ancient redwood. You cannot simply point a telescope at a single white dwarf and wait. Human civilization would rise, fall, and be forgotten in the dust long before the first glimmer of crystallization even began. The task seemed impossible, a direct confrontation with the sheer scale of cosmic time. If we couldn't watch one star complete its journey, we would have to find another way to see the story. The initial excitement gave way to a sobering reality. The theory was a masterpiece of physics, but it was stranded on an island cut off from the mainland of observational proof. To build a bridge, we would need new tools, new methods, and a perspective so broad it could encompass the entire galaxy. The era of speculation was over. The era of cosmic cartography of stellar archaeology on an unprecedented scale had to begin. The answer, it turned out, was not to stare harder at a single point of light. It was to open our eyes to hundreds of millions of them. This grand undertaking required a new kind of observatory, one designed not just to peer into the depths of space, but to conduct a census of our entire stellar neighbourhood. It would be a mission to map our corner of the universe with a precision that would have been considered sorcery just a generation prior. This mission was Gaia. Launched by the European Space Agency, Gaia wasn't built to hunt for exotic phenomena in the distant universe. Its objective was in a way more profound: to create the ultimate three-dimensional map of the Milky Way. For years it has orbited the Sun, its twin telescopes spinning slowly, methodically, scanning the entire sky over and over again. Each sweep captures the position, the brightness, and the motion of over 1 billion stars. Imagine trying to create a perfect map of a sprawling, chaotic city by taking snapshots from a moving train. This is the challenge Gaia faces as our Sun and every star it measures is hurtling through space. To solve this, Gaia measures each of its target stars dozens of times, building up a motion picture of their journey through the galaxy. By measuring their apparent shift against distant background objects as Earth orbits the Sun, a phenomenon called parallax Gaia can calculate their distances with breathtaking accuracy. And once you know a star's true distance, you unlock its secrets. You can determine its true luminosity, its intrinsic brightness, distinguishing a truly brilliant star far away from a dim one that is merely close. For the scientist hunting for cosmic diamonds, this was the key. Gaia's data stream was a torrent, a deluge of information. Within this cosmic phone book containing the vital statistics of a vast portion of our galaxy was a treasure trove of white dwarfs. Not dozens, not hundreds, but hundreds of thousands of them. Each one a tiny dying ember now catalogued with its exact position, its motion, its temperature, and its luminosity. This was the raw material for a revolution. Using the well-understood laws of stellar evolution, astronomers could now take Gaia's precise measurements and work backwards, calculating the mass and, crucially, the age of each white dwarf. They could finally sort them, lining them up not by their position in the sky, but by their position in time. Suddenly, the impossible problem had a solution. We no longer needed to watch a single star for 10 billion years. Instead, we could take a snapshot of the entire population at once. Imagine having a photograph of every person in a giant city. By arranging them in order of their age from infants to the elderly, you could piece together the entire story of a human life without ever watching a single person grow up. This is what Gaia allowed us to do for stars. We could now see young, searingly hot white dwarfs, their substance still a turbulent, exotic fluid. We could see middle-aged ones having cooled for billions of years, approaching the critical temperature where the metamorphosis should begin. And we could see the ancient ones, the dim Methuselahs of the galaxy, so old and so cool that their hearts should by all rights be solid. The data from Gaia was the grand framework, the Galactic Family album, that showed us the beginning, middle and end of the story all laid out at once. But it was still an indirect view, a look at the surface. To confirm the theory, to truly know what was happening deep inside, we needed a way to listen. We needed a way to hear the heart of a star beating. This is the strange and beautiful science of astroseismology. Just as seismologists on Earth study earthquakes, to map the hidden layers of our planet's interior, astronomers can study starquakes, to probe the invisible depths of stars. Many stars, including some white dwarfs, are not perfectly stable. They pulsate, they throb, they vibrate in complex rhythms like cosmic bells rung by the forces churning within them. These pulsations are not random. They are harmonic waves, sound waves of a sort that travel down into the star's core, bounce off its different layers, and return to the surface, subtly changing the star's brightness. These are incredibly faint signals, a flicker in brightness of just a few parts per million. Detecting them requires telescopes of exceptional stability and patience, staring at a single star for weeks or months on end, catching every photon to trace the gentle rhythmic rise and fall of its light. For our diamond hunters, this was the ultimate diagnostic tool. A sound wave travelling through a liquid behaves very differently from one travelling through a solid. You can hear the difference yourself. A tap on a glass full of water sounds entirely different from a tap on a block of ice. The ice, being a crystal, carries the vibration cleanly at a higher frequency. The water, a fluid, dampens it, changing its tone. Astroseismology allows us to do the same for a star 50 light-years away. The pulsating waves echoing within a white dwarf carry a signature. Their frequencies, their patterns, their very character are a direct report from the core. They tell us about its temperature, its density, its composition, and most importantly, its physical state. A fully liquid white dwarf would have a certain set of resonant frequencies, a specific song. But a white dwarf that has begun to crystallize, that would be a different instrument entirely. It would have a solid heart, a crystalline core, and the waves that travelled through it would be changed. They would be altered by this new solid medium, creating new frequencies in the star's song, a subtle but detectable shift in its celestial music. The search was on for this telltale signature. It was a painstaking process, listening to the faint whispers of these dying stars, deconstructing their complex light variations into their constituent frequencies like a sound engineer, isolating every instrument in a grand orchestra. And slowly, star by star, the evidence began to build. Astronomers found pulsating white dwarfs whose vibrations simply could not be explained if their interiors were entirely fluid. The models only matched the observations if you included a solid crystalline core of a specific size. For one star, the model suggested a solid core containing maybe 10% of its mass. For another older and cooler, the models required a core of 30%. For yet another, the data pointed to a heart that was over 80% solid diamond. We were no longer just looking at the surface. We were mapping the interior. We were detecting the solid crystal hearts of dead stars. The footprint in the desert now had a voice. And it was singing a song of crystallization. But even with this wealth of new data from Gaia and astroseismology, the path forward was fraught with immense complexity. Observing a phenomenon is one thing. Fully understanding the physics behind it is another challenge entirely. The interior of a white dwarf is one of the most extreme environments in the universe. The pressures are 1 billion times greater than at the bottom of Earth's deepest ocean. Matter exists in a state called electron degenerate, where the rules of quantum mechanics prevent atoms from being crushed any further, creating a substance far denser than anything on Earth. A teaspoon of it would outweigh a fleet of battleships. How does crystallization actually proceed in such an alien place? Building a computer model that could accurately simulate this process was a monumental task, pushing the boundaries of computational astrophysics. Scientists had to account for every subtle detail. The simple picture of a pure carbon core was a useful starting point, but reality is always messier. White dwarfs are mostly carbon and oxygen, but they also contain trace amounts of other elements. Neon, magnesium, iron left over from the star's former life. How would these impurities affect the crystallization? Just as impurities in water change its freezing point, these trace elements could dramatically alter the temperature and pressure at which the cosmic diamond lattice begins to form. Some models suggested that as the carbon and oxygen crystallized, heavier elements like neon might be squeezed out, sinking towards the center in a kind of elemental rain, releasing even more gravitational energy and further complicating the cooling process. The structure of the crystal itself was a matter of intense debate. Would it form a simple clean lattice, or a complex multi-layered structure like a planetary gobstopper of different crystalline forms? The models had to be refined again and again, each new version tested against the torrent of observational data. It was a constant iterative dance between theory and observation. The observations from Gaia would constrain the ages and masses, while the astroseismic data would provide a direct glimpse of the interior structure. If a model couldn't reproduce the pulsations of a real observed star, it was wrong. It had to be discarded or improved. This process weeded out the flawed ideas, forcing the models to become an ever more faithful reflection of reality. It was a global effort with teams of theorists and observers working in synergy, pushing each other forward. The puzzle was being assembled piece by painstaking piece from the cold, hard light of 1,000 distant stars. And then with all the pieces in place, the grand picture finally emerged. It was a moment of stunning, breathtaking clarity. By combining the hundreds of thousands of white dwarfs mapped by Gaia with the detailed interior models refined by astroseismology, scientists could finally perform the ultimate cosmic magic trick. They plotted every single white dwarf on a diagram, a celestial chart mapping their luminosity against their colour or temperature. And as they did, a pattern began to appear. A traffic jam. On this chart, where stars should have been smoothly and predictably fading out, there was a pileup, a distinct region where there were far more white dwarfs than the standard cooling models predicted. They were lingering, their journey into darkness paused. This was the echo of that very first clue, now seen not in a handful of stars, but across a vast population, an undeniable feature of the galaxy. This was the signature of the latent heat of crystallization writ large across the cosmos. But now they could go deeper. Using the ages they had calculated for each star in this cosmic traffic jam, they could map precisely where this slowdown began and ended. They could see that stars entered this pileup when they reached an age of around 1 to 2 billion years, and they could see that they lingered there for a staggering amount of time, up to another 2 billion years before resuming their cooling. The energy being released was immense, powering these dead stars for longer than life has existed on Earth. The scale of the process was finally laid bare, and with the astroseismic data they could add the final crucial layer. For the stars just entering this traffic jam, their pulsating hearts revealed small nascent crystals. For the stars in the middle of it, the solid cores were larger, more developed. For the stars emerging from the other side, the data showed hearts that were almost entirely solid. They could finally map it. The crystallization front. They could see how this boundary between liquid and solid, this shimmering surface of transformation, began at the very centre of the star and slowly over eons moved outwards. They could track its progress not in a single star but across the entire population. By looking at a 10 billion year old star, they were seeing the future of a 1 billion year old star. The story was complete. The theory was no longer stranded. The bridge between speculation and reality had been built, forged from the light of 1 million stars and the relentless ingenuity of the human mind. We were now in a very real sense watching it happen. Across the grand canvas of the Milky Way, we were finally witnessing the slow, majestic and universe-altering birth of a diamond star. And this revelation, this confirmed reality, would force us to reconsider everything we thought we knew about the ultimate fate of the stars and the very future of the universe itself. And so, the stage was set. We had the ghosts in the machine, the tantalizing theoretical models of a star slowly freezing into a solid. We had the celestial messengers, the precise torrent of data from missions like Gaia, charting the positions and luminosities of 1 billion stars with breathtaking accuracy. We even had the faint rhythmic pulse, the stellar heartbeat recorded by probes like the Transiting Exoplanet Survey Satellite, or TESS, listening for the secrets hidden within the light. But these were separate streams of knowledge tributaries flowing in parallel, each powerful but incomplete. They told us what was there, and they gave us a theory for how it worked, but they couldn't yet show us the process in action. The ghost remained a ghost. The challenge was monumental, to merge these streams into a single thundering river of understanding, to build a bridge between the abstract world of pure mathematics and the tangible reality of a dying star hanging in the void. How could we possibly combine the spectral fingerprints of a star, its precise distance from Earth, its subtle, almost imperceptible vibrations, and the theoretical physics of matter under crushing pressure to create not just a snapshot but a moving picture? How could we turn a collection of disparate facts into a coherent unfolding story, the story of a diamond being forged in the heart of a stellar corpse? The first step was to tame the data deluge, to see the individual trees for the forest. The Gaia spacecraft had given us the cosmic equivalent of a hyper-detailed census. For hundreds of thousands of white dwarfs, we suddenly knew their exact address in the galaxy, which allowed us to calculate their true intrinsic brightness, stripping away the dimming effects of distance. This was the master key. A star's brightness is a direct window into its energy output, and for a white dwarf, energy output is simply a measure of how fast it's cooling down. It's like knowing the precise temperature of a cooling ember. From that, you can begin to work backwards to estimate how long it has been cooling. But this alone wasn't enough. It gave us a vast catalogue of stellar temperatures, a ledger of cosmic cooling, but it was still a static picture. We could see the so-called pile-up, that strange stellar traffic jam where white dwarfs seemed to linger at a specific temperature and brightness, refusing to cool down as predicted. This was the great clue, the smoke that hinted at a hidden fire, but we couldn't see the flames. The data from Gaia was a map of the crime scene, but it didn't show us the perpetrator in the act. We needed a witness. That witness was astroseismology, the revolutionary science of studying a star's interior by listening to its vibrations. Probes like TESS, designed to find planets by watching for the minuscule dimming of a star's light, were also perfect for this kind of celestial eavesdropping. They could stare unblinking at a single patch of sky for weeks on end, measuring changes in brightness so small parts per million that they were previously undetectable. For a certain class of white dwarfs known as pulsating white dwarfs, these flickers are not random noise. They are the visible manifestation of immense waves, sound waves of a sort, sloshing around deep inside the star. These waves travel through the stellar plasma, bouncing off different layers, their speed and frequency altered by the density, temperature, and composition of the material they encounter. It is the cosmic equivalent of a physician tapping on a patient's chest to determine what lies beneath. These vibrations are a star's autobiography written in the language of light. The problem was that reading this language was like trying to understand a symphony from a single distorted note. The signals were incredibly faint, buried in noise, and their meaning was wrapped in the impenetrable physics of degenerate matter. We had the sound, but we couldn't yet understand the words. Here in this impasse between observational power and theoretical understanding, humanity deployed one of its most formidable tools, the supercomputer. We couldn't go to a white dwarf. We couldn't scoop up a piece of its core and study it in a lab. So we built one ourselves, not out of matter, but out of mathematics. Inside the silicon hearts of these computational behemoths, scientists constructed digital universes, virtual laboratories, where they could forge white dwarfs from the ground up. They could program the fundamental laws of physics, gravity, quantum mechanics, thermodynamics, and watch as a star evolved over billions of years in a matter of weeks. These were not mere cartoons. They were staggeringly complex simulations, each one a universe in miniature, tracking the interactions of trillions upon trillions of virtual particles under conditions of pressure and density that defy all earthly intuition. It was within these digital crucibles that the ghost in the machine could finally be given form. Scientists could build a virtual white dwarf, a perfect sphere of superheated carbon and oxygen plasma, and command it to cool. They watched through the eyes of their code, as the temperature in its core slowly dropped over billions of simulated years. They saw it reach that critical threshold, that magical tipping point, where the chaos of the liquid state could no longer resist the crushing embrace of gravity. And then they saw it happen. The crystallization began. Not as a single instantaneous event, but as a slow, inexorable wave of transformation. Deep in the core, where the pressure was most intense, the first few atoms would lock into place, forming a microscopic seed crystal. This was the moment of conception for the cosmic diamond. From that initial seed, a solidification front would begin to sweep outwards, a creeping frontier between the liquid and the solid. And as this front advanced, the simulation revealed the critical secret, the phenomenon that explained everything, the release of latent heat. Just as freezing water releases a tiny burst of energy as it turns to ice, the crystallization of carbon and oxygen, plasma releases a colossal amount of thermal energy. This energy, this heat of transformation, acts like a celestial blowtorch warming the star from the inside out. It serves as a powerful brake on the cooling process. The star, which should have been fading into obscurity, is temporarily reinvigorated by its own internal freezing. The simulation showed in vibrant, quantifiable detail how this process would create a pause, a lingering in the star's cooling journey. It would cause a stellar pile-up at a very specific luminosity and temperature exactly matching the mysterious traffic jam observed by Gaia in the real galaxy. The ghost in the machine had cast a shadow, and that shadow perfectly matched the evidence from the crime scene. This was the watershed moment, the fusion of theory and observation into a single unified vision. The simulations became the key, the Rosetta Stone that allowed astronomers to finally translate the cryptic language of stellar light. They could now build a comprehensive library of simulated white dwarfs at every conceivable stage of crystallization, a model of a star that was 10% solid, 30%, 70%, 95%. For each of these models, they could precisely calculate what its signature should be. They could predict its exact surface temperature, its absolute brightness, and most importantly, how its internal structure would affect the pulsating waves rippling through it. Each stage of freezing, they discovered, would imprint a unique fingerprint on the star's vibrations. As the solid crystalline core grew, it would fundamentally change the star's internal acoustics. The sound waves of the astroseismic pulses would travel differently through the rigid diamond-like lattice than they did through the supple plasma. This symphony of the star would change its tune as it froze. The simulations provided the sheet music a complete score for the entire life cycle of a crystallizing white dwarf. Now armed with this powerful predictive tool, astronomers could turn back to the sky. They could take the real messy, noisy data from a single pulsating white dwarf observed by TESS and lay it against their library of simulations. It became a cosmic matching game of unprecedented scale and precision. They would ask the computer, does the frequency spectrum of this real star, this faint point of light millions of trillions of miles away, match the simulated spectrum of a white dwarf whose core is 38% solid? Or is it a better match for one that is 42% solid? The process was painstaking, a computational brute force attack on the mysteries of the cosmos. For each candidate star, they would run thousands of simulations tweaking the parameters, the star's mass, its age, its composition, until the virtual star's light signature was an identical twin to the light signature of the real one. They were no longer just observing, they were diagnosing. They were performing a non-invasive cosmic biopsy, peering deep into the heart of a star to determine its physical state. And the results were staggering, a revelation that transformed the field of stellar astronomy overnight. They could now point to a specific star, a white dwarf catalogued as WD J194 Plurifib 4012, for example, and state with unnerving confidence that its core is approximately 86% crystallized. They could look at another BPM 370093 and determine that the wave of solidification has reached about halfway to its surface. These weren't guesses or estimates based on broad categories anymore. This was a specific quantitative measurement of an ongoing physical process inside an object so remote it defies imagination. They could effectively place a thermometer in a star's core and watch the mercury drop and then see it pause as the star's own freezing warmed it from within. They could, for the very first time, create a real-time map of this incredible transformation. By observing dozens, then hundreds of these crystallizing white dwarfs, they could piece together the entire evolutionary sequence, arranging them in order, like single frames from a very, very long film. Here is a star just beginning to freeze its core, a mere seed of diamond. Here is another billions of years older, almost entirely solid, its pulsations telling the story of a rigid crystal lattice that fills nearly its entire volume. This convergence of data and computation had finally given us the ability to watch the unwatchable. We were now witnesses to one of the most serene and profound transformations in the universe. We could trace the complete journey from a seething, turbulent ball of plasma, a remnant of a sun-like star's fiery life, through its long, slow cooling. We could see the exact moment it reached the freezing point, the point where the elegant order of the crystal lattice triumphed over the chaos of thermal motion. We followed the slow, outward march of the solidification front, an epoch-spanning process that releases enough energy to delay the star's final fade into blackness for up to 2 billion years. And we could see the end state, a celestial jewel, a sphere of crystallized carbon and oxygen trillions of times denser than a diamond on Earth, humming faintly with the last vestiges of its ancient heat. Humanity, through the sheer power of its curiosity, its ingenuity, and its relentless drive to understand, had learned how to watch a star turn into a diamond. We had pieced together an event that unfolds over a timescale that dwarfs our own existence, and we had done it by learning to listen to the whispers of starlight and by building new universes inside our own machines. The picture was now complete, the puzzle solved with a clarity that had once been the sole province of science fiction. The strange dimming, the unexpected warmth, the subtle stellar pulses, all were now understood as chapters in a single epic story of cosmic alchemy. This was more than just an astronomical curiosity. It was a fundamental breakthrough in our understanding of the ultimate fate of stars like our own sun. We'd confirmed a bizarre prediction of quantum mechanics not in a terrestrial laboratory, but in the untamed wilderness of the cosmos itself. We had witnessed the final glorious act in the life of a star, the slow, silent and incredibly beautiful process of its final rest. This achievement represents a new maturity in our relationship with the universe, a capacity to move beyond simple observation and engage in a true dialogue with the stars. We had learned to read their history, diagnose their present condition, and predict their ultimate future. But with this newfound power comes a profound new opportunity. For in learning to read the age of these stellar relics with such exquisite precision, we realized we hadn't just found a diamond in the sky. We had found a clock. And with this cosmic clock, this celestial ledger of time itself, we could now begin to ask even bigger questions. We could begin to date the very components of our own galaxy, to measure the age of the spiral arms, the ancient star clusters, and perhaps even the universe itself. The story of the diamond star was complete, but it was also a key unlocking a door to an even grander mystery. And so, the long vigil ends. The signal we have pursued across the light years, the faint rhythmic pulse that has been our guide, has finally delivered its definitive message. What began as a whisper in the esoteric language of quantum mechanics, a ghost haunting the equations of stellar evolution, is now a confirmed observable truth. The star has turned. The transformation we set out to witness, a process so monumentally slow, so alien to our fleeting human timescale, has crossed a detectable threshold in its magnificent unhurried journey. Deep within that stellar remnant, in the crushing dark of its core, a phase transition of unimaginable scale is underway. Carbon, the very element of life, is relinquishing its fiery past, its atoms locking into a rigid geometric embrace. The heart of a sun is crystallizing. It is becoming a diamond, a cosmic jewel the size of a planet, forged not by fleeting pressure in the Earth's mantle, but by the slow, patient and inexorable cooling of a stellar ghost. The light we gathered, filtered through instruments of staggering precision, carried the signature of this grand metamorphosis. It told a story not in words, but in the subtle shifts of its oscillation, a celestial ringing that changed its tone as the core solidified, much like the sound of a bell changes when its structure is altered. The data, once a torrent of abstract numbers and wave patterns, has resolved into a breathtaking chorus of confirmation. We have in a very real sense performed stellar seismology on a dying sun, listening to the deep vibrations of its final transformation. We have watched the impossible become the inevitable. Reflecting on this moment requires us to look back on the path we have travelled together. This was a journey that began not with a telescope, but with a thought experiment, a bold question asked in the quiet halls of academia. Could the universe, in its infinite creativity, truly perform such an act of cosmic alchemy? The theory was elegant, a beautiful confluence of thermodynamics and particle physics. It predicted that white dwarfs, the dense embers left behind by sun-like stars, were not destined to fade into an amorphous, unremarkable darkness. Instead, as they radiated their residual heat over billions of years, their cores under pressures 1,000,000 times greater than Earth's centre would reach a critical tipping point. The free-flowing plasma of carbon and oxygen nuclei, a super-dense fluid of unimaginable properties, would begin to freeze, not into ice but into a crystal lattice of staggering density and order. This prediction remained a piece of beautiful, unproven mathematics for decades. A lovely idea, but one that seemed destined to remain beyond our grasp. A cosmic event happening on a timescale that mocked our own brief existence. How could we possibly watch something that takes millions of years to get underway and billions more to complete? It was a challenge not of distance but of time itself. We were trying to perceive a geological process on a stellar scale, to see the motion of a glacier when our own lives are but the blink of an eye. Yet humanity's genius lies not in outliving the universe, but in outthinking its limitations. The solution, as you have seen, was one of profound ingenuity. We realized we didn't have to watch one star for 1 billion years. We could instead survey hundreds of thousands of them, capturing stellar snapshots at every different stage of this cooling process. By finding white dwarfs of various ages and temperatures, we could assemble the story frame by frame, creating a time-lapse movie of stellar evolution, with each star acting as a single frozen moment in the grand narrative. This led to the creation of celestial cartographers' automated sky surveys that mapped the galaxy with tireless precision, building a library of stellar embers. From this vast cosmic census, we identified our candidate. It was a white dwarf that our models predicted was right on the cusp, a star poised at the exact moment of crystallization, the perfect celestial laboratory for our audacious experiment. It was old enough to have cooled to the critical temperature, but not so old that the process was already complete and hidden from view. The quest then shifted from discovery to observation. We turned the most powerful instruments ever conceived toward this single point of light, this tiny fading spark in the cosmic darkness. We witnessed the immense collective effort, the collaboration across continents and oceans, as observatories synchronized their efforts, listening for the subtle song of that distant crystallizing core. The technical hurdles were immense, bordering on the impossible. We were trying to detect minuscule variations, a flicker within a flicker, from a source trillions of kilometers away. It required us to filter out the noise of our own planet's atmosphere, the interference from our own technology, and the constant chaotic chatter of the universe itself. It was an act of cosmic archaeology, sifting through layers of light to find the one pure signal, the echo of a star's heart turning to stone. And then, after years of patient gathering, of refining the data, of pushing the very limits of what our technology could perceive, the pattern emerged. The oscillations slowed down in precisely the way our models predicted they would, if a vast portion of the star's interior was solidifying. The evidence was irrefutable. The theory born on a blackboard had been validated in the crucible of space. This journey from a speculative whisper to a verifiable cosmic reality is more than just a scientific triumph. It is a profound statement about our place in the cosmos. We are a species defined by curiosity, driven by an insatiable need to understand the grand stage upon which we exist. We build extensions of our senses, magnificent machines of glass and silicon, not as weapons, but as tools of pure discovery. They are our collective eyes and ears, allowing us to perceive realities that are otherwise completely inaccessible to our fragile biology. This real-time observation was never about seeing the diamond with our own eyes. It was about achieving a deeper kind of sight, the ability to read the language of light, to interpret the vibrations of a star, and to construct a complete, verifiable picture of a hidden internal process. It is a testament to the power of the scientific method, that rigorous self-correcting process of hypothesis, prediction, and verification that allows us to grasp phenomena that dwarf our own existence. We did not see a star turn into a diamond. We understood it into reality. We assembled the truth from the faint echoes and subtle clues the universe provides to those patient and clever enough to listen. This act of cosmic comprehension changes our perspective forever. We are not merely passive observers of a pre-written cosmic play. We are active participants, decoders of the script, capable of understanding the most fundamental processes of creation and decay. This discovery is not just about a single distant star. It is a profound and deeply personal glimpse into our own ultimate future. Because the star we have been watching is a ghost of what our own sun will one day become. For 5 billion more years, our home star will continue to burn, fusing hydrogen into helium, bathing our solar system in life-giving energy. But it too is mortal. Eventually, the hydrogen fuel in its core will run dry. Our sun will swell into a magnificent, terrifying red giant, its outer layers expanding to engulf the inner planets, perhaps even our own Earth. It will be a final brilliant act of cosmic grandeur. After shedding its outer atmosphere as a beautiful planetary nebula, its core will collapse under its own immense gravity. It will shrink down into a new form, an Earth-sized object, containing nearly half the sun's original mass. A white dwarf. Our sun, the source of all our light and life, will become one of these stellar embers, glowing with the residual heat of its long life. And then it will begin the same slow, patient journey we have just witnessed. over a timescale so vast it beggars the imagination. The remnant of our sun will cool. Its light will dim from a brilliant white to yellow, to a deep orange, and finally to a dusky sullen red. And as it cools, the pressure in its carbon-oxygen core will mount until it too reaches that critical threshold. The atoms will lock together. The heart of our solar system will begin to crystallize. The star that warmed our skin, that drove our weather, that fueled all of biology, will in its final act transform into a colossal diamond sphere, a silent, glittering monument floating in the cold darkness of space. There will be no one left here to see it. Humanity will be long gone, having either perished or journeyed to other stars. But knowing that this is the fate of our star changes how we see it now. It is not just a ball of fire. It is a dynamic entity, a creature with a life cycle, a history and a future. Its final form will not be one of dreary, empty decay, but one of incredible ordered beauty. A quiet, crystalline perfection that will endure for trillions of years perhaps, until the universe itself grows cold and dark. This knowledge imbues our connection to the sun with a new sense of the profound. We are living in its brilliant, energetic youth. We are the beneficiaries of its fiery middle age. And now, thanks to this incredible journey of discovery, we can envision its distant, spectacular end. We have seen the ghost of our own sun's future. This understanding elevates the stars from mere points of light into characters in the epic story of the cosmos. They are not static decorations on a celestial sphere. They are the universe's engines of transformation. In their fiery hearts they forge the heavy elements from which planets and we are made. The carbon in our bodies, the oxygen we breathe, the iron in our blood, all were created in the thermonuclear furnaces of stars that lived and died long before our sun was even born. We are quite literally stardust. And in their deaths, they continue to transform. The most massive stars explode in supernovae, seeding the galaxy with the building blocks for new generations of stars and life. The less massive stars, like our sun, embark on this slower, more elegant path, ending their lives as these titanic crystalline structures. It reveals a universe that is constantly recycling, constantly reforming itself, where even the end of a star's life is not an end to its story, but the beginning of a new, enduring and beautiful chapter. The diamond star is not an anomaly. It is a destination. It is the ultimate fate for more than 97% of all stars that have ever existed or will ever exist. The universe, it seems, is destined to be filled with these dark, glittering jewels, the final, silent testaments to the lives of countless suns. And so, we are left with a final, humbling realization. Our pursuit of knowledge, our relentless drive to unravel these cosmic mysteries, is the most profound expression of our existence. We are a brief flicker of consciousness in an ancient, vast universe, yet we have developed the means to comprehend its grandest designs. We have learned to look into the darkness and see not an empty void, but a tapestry of physical laws and unfolding stories. The quest to witness a star crystallize was once a fantasy, a dream confined to the pages of science fiction. Today it is a recorded observation, a chapter in our textbooks. This is the true power of our journey. It demonstrates that with patience, with collaboration, and with boundless ingenuity, there are no secrets the universe can keep from us forever. The impossible is merely that which we have not yet learned how to observe. The story is not over. For every question we have answered, a dozen new ones have taken its place. What other exotic states of matter lie hidden in the hearts of stellar remnants? What other subtle messages are being carried on the ancient light from distant stars, waiting for us to build the instruments and the imagination required to decode them? The universe is patient. It will hold its secrets for as long as it must, but it will not hold them forever. Because the same cosmic forces that forge the diamond stars also forge the human mind, and that mind, once set upon a course of discovery, is the most relentless and powerful force of transformation we know. The search will continue. The vigil will never truly end.